So the content of this talk is a short introduction and some background information about Geant4 and QSS, and then the implementation of QSS inside the Geant4, then some earlier result and the status of this project. So the motivation of this work is the simulation involved the numerical solutions. The good example is the charged particle, the moving, the non-uniform magnetic field, so that you have to define the approximation of position to the next the position and also directions. And also when the particle crosses the boundary, it's actually tracking stars because the material usually change. So you have to actually initialize those the physics from that point. And the traditional method, usually the high energy detector is complicated. So there are frequent discontinuity, and where we find this intersection point, which takes quite a bit of the CPU times. And the quantized state system method is the modern family of numerical integration, which exhibits quite an interesting feature that can be applicable to the high energy simulations, which we're going to talk about their characteristics in a couple of slides later. And the goal of this project is basically try to develop a proof of concept implementation of QSS inside the Geant4, and also address suitability as an alternative the integrator, and also evaluate the performance. So the Geant4, as you may know, is a mostly widely used simulation toolkit in the high energy physics as well as other domains, and provide the classical numerical method based on the time discretizations. So this is usually known as a Lunga-Kutta family. The most the famous one is a fourth order. The downside of this Lunga-Kutta is the efficient, but it sometimes involve the iterative algorithms. So in the modern computing, you do the affiliation or the GPU application. So that's sort of the ill feature you cannot avoid. And in case you cross many boundaries, so it takes a lot of time to find also to meet the accuracy you require, also the discontinuity by boundaries. So in the Geant4, the typical the numerical step is involve usually the 11 right-hand side of evaluation of the Lorentz equation, basically, for the force of the Lunga-Kutta. So the idea is so you imagine this, the field is the non-uniform. So you have to find this is the initial position, and physics propose the moving step h. So basically that's the next interaction point. And then normally you do one fixed step, which involves actually for evaluation of a right-hand side. So you principle you go to in the middle, and you evaluate the position and the velocity with new values of a magnetic field from that point, and go to the next point. And the second one is you divided by that the half step. So each of these again involve a full evaluation of that. So in the final actually the truncated error is the difference between them. So if this is smaller than something, okay, you move from here to there. And if not, you break actually the segment with a smaller piece, so that you repeat the approximation again. So this is basically the iterative the process. The second one is if you cross the boundary, for example, if your final position in the other side of the volumes, then you need to find the exact sort of the position where it crossed the boundary, so that you start the new tracking from here again. So that usually also iterative process, because you have to sort of based on this straight line, the approximation point in the curved position. So you move to that ratio and coming back and until you have the precision which you require. So the QSS method is the completely different approach. Is based on the state the variable quantizations. So like the Lunga-Kutta family, which is basically you move X and you see the variation either in the position or the directions. And the QSS, you can think it's a reverse way. Actually, you actually move the size that you want to, and then actually your time you stop at the time actually give it the solution of the state variable and the change of the quantum the variations. So this continuous state variable is divided by the smaller piece, basically is a quanta. And the ordinary the differential equation basically let's take X is either position or velocity. So that your state variable change by actually quantized quantity, which for the first order cases, this is basically nothing but the piecewise step functions. And if it is a second order, it will be linear approximations. And the third order is the second order polynomial, and so on. So this delta Q is the basically maximum deviation allowed between the continuous the variable X and the quantized the changes, which basically control the errors and the precision decided by users. And the higher order, basically the extension of the polynomial. And this was used in the many other fields. So the good features is asynchronous and also very lightweight. The handling of discontinuity is basically finding root between the polynomial and the given equations. And also there are all information in the between them is applied in many different areas with involving the many state variables and they show up quite a bit of speed up pairs. And the QSS solver is basically standalone collection of actually QSS the method and implemented with C, and it also provide the traditional algorithms like the Donan Prince method and so on. And GQLink is basically interface the available QSS method in the QSS solvers. So before move to the realistic problems, the showing here is the exact the setup the setup have exact solutions. So basically particle moving in the uniform magnetic field, so that you can actually calculate the solution exactly. And so the purpose of this exercise is understanding the performance and also error, the error controls. So the showing here is basically comparing the error between the Geant4 simulation and the QSS, which is basically dotted line, and the simulation time is solid, Geant4 and the QSS solver. So certain use this setup, if you have a crossing around the 2000 plane, also moving to the 100 meter, so the QSS shows a sort of quite a bit of a performance gain at 200 plane cases. So the QGLink is nothing but actually interface between Geant4 and the QSS the solver, which is a standalone. So basically the API is try to minimize the communication between these two, and also QSS in this case is try to control the particle the propagation within the QSS solver. So the one good thing is the QSS basically because it is quanta basically define global errors. In Geant4 cases, usually errors accumulated and it can getting the growth as the stepping goes on. So the high-level diagram is very simple. The Geant4 has a collection of the traditional the numerical method, and the QSL solver, the QSS family plus or some of other traditional. So basically, QGLink is basically the bridging games. And the boundary detection in Geant4, as I explained, it involves also iterative procedure depend on how adaptive step control goes. So there is basically three features. Is okay, you should know where you are, and also what is the straight line from the beginning and the end, and also the iterative method the finding the intersection point at the boundaries. In QSS is a much finding the intersection point is much cheaper because it it has for example the higher order, it is the polynomial, and then you have a plane of geometry and try to solve basically the root of the equation between those two. So some test result is using CMS geometry. So we thought that this is sort of complicated enough. And also the sort of nihilistic the magnetic field accepted from CMS-SW. And two test cases is one is the single particle, the 10 GeV pions. The second case is the fixed GZ at the LHC energies. And showing the bottom here is for the pion cases, the total number of the pi minus steps for 10,000 events. And also this is the total number of the secondary electron steps. So the idea here is basically because we cannot directly compare two cases absolute way, but statistically they are sort of agree each other. So which gives some baseline validation of this method. And the performance-wise, this is a simulation time versus the number of events to simulate. And GQLink currently around 70% slower. Also, that is also quite similar in the realistic event. So the main bottleneck is the QSS usually design for the continuous process. In the head simulation, because it's a physics, because sometimes you lose energy and you have a different initial conditions. So then the QSS solver actually reinitialize its engines, which takes because they have to evaluate all these spatial variables again at new points, which is the main bottleneck. So we try to actually remove that overhead, and so they expect improve some performance later. And so to go there, we also test a simple scenario. So this is turning off basically physics, and also much similar, the simpler the trajectory, and the comparing to the standard sort of default Geant4 the stepper, in certain cases the QGLink can demonstrate actually is faster in with involving many planes. So the main focus is now so far we use this boundary detection with the Geant4 actually method. So we like to remove that, and using the full QSS capability, the finding the efficient boundary the crossings. So there was one of the main motivation of this, and the second one is because this method in general does not involve any iterative method, so it will be much suitable to apply the parallel the computing technique here. And so the details is the first step is we'd like to convert actual or Geant4 solid with passive the polyhedrons. So this is basically aided by other the geometry package, and then find the intersection point, the analytical with QSS polynomials, and it could involve many detailed treatment to get the final sort of efficient the algorithm. For example, you can move to the Geant4, for example, in Geant4 term there is the safety, so which means you are sure you are not crossing the boundary. So the QSS move to there without any interruptions, and from there you can use, for example, linear segment joining the final position, and the first maybe the candidate is what the linear segment hit at the boundary, and try to solve the route between that target, the face, and the QSS polynomials. So the conclusion is this is still ongoing work, and implement basically the interface between QSS solver and Geant4, and they did some early validations. So the performance-wise is around 20% slow, but we promise to understand where the bottleneck is, and but this is, I think, a good step. We have tools, and will improve many different, I think, experimental cases. Okay.
Questions for discussion? In this analysis, the trajectory of the charge path itself is the same for Geant4 and the QSS, or they are different in the trajectory itself.
Trajectory should be the proposed step, which is provided by physics. That is the thing. And then,
So it does not, the method does not affect the physics mode.
Right. But you should start with you should know how much actually you apply, right? That will be given by the physics models, physics processes. But the way the Geant4 does is the jump is discrete steps, and the QSS actually move to how much it actually change, so that will define final the intermediate point. It can be go to the final, depend on how much it apply. It could be many steps also. But in Geant4 it actually moved to the end first. Then they evaluate the error. So if the error is big, then you have to actually break from backward, right? So it's a completely, I think, different trade-off. But the QSS will give the certain the defined actually the step, which not involving uncertainty how many you actually you have to break.
And the efficiency depends on the quantum delta Q.
Right.
You have some optimization to set the values of delta Q.
In Geant4, it definitely it is the user actually set that one. The default is 10 to the minus 5, and initially you can set the delta Q as the same middle, but in QSS is equivalent to also global error, right? Once you set the quantum, the accumulated error cannot be bigger than that. But Geant4 is the error is by one step, right? So if you deviate a little bit and the analysis step deviates a little bit, and it actually accumulates. So it's the Geant4 error is local error, and QSS is global error. That's also the difference between them.
Okay. I see no further questions. Then
thank you.
Let's thank the speaker again. And we'll move to the next talk.